So to starting evaluating what's happening here, we will activate the faceplate, and the faceplate shows to us the set point, the present value, and the opening of our controller. And we will add also the strip chart, because the strip chart helps us to identify what's happening in terms of graph. So here, by standard, I will use the set point, the PV, and DOP. It's very important when you are evaluating PID tuning that you observe not only the PV reaching the set point, but also the opening of the valve, because when you are doing a PID manual tuning, observing the behavior of the opening of the control valve, you have the feeling to know if you need to increase the KP, or if you need to increase or decrease the TI, and etc. So I always use also the OP as a variable that I observe when I doing the PID tuning of a control loop. So we need just to click on create and display. What is interesting to you know, if you don't know yet, when you click with the right button of your mouse, you have the option to do the dockable of this window. So I will use that, and I hold this. I can let this at my right side or left side, wherever I want to, what the region that best fits for me. And I will do the same for the LIC controller. So in this case, we have a direct controller. Remember, if my variable increases and I need to increase the opening of the control valve, I have a direct controller. So to return to the set point. So this is a rule of thumb and depends on a lot of characteristics of the system. And here I have also in this case, as I'm talking about level, my level is from 0% to 100%, and I have here the PID parameters, and for a while only the KC is available, and I will change that for Yokogawa, because this way I have the KP. With exception for Foxborough, here the others algorithm type use the same value. So if I change from KC to KP, it keeps the same value, but when I use the Foxborough, the calculations are different, so they use different values. So now what I will do is the same thing. Add the faceplates to the process simulation and also a strip chart. Create and view, and I will dock this also, and I can use the same part of the screen to share two graphs in my screen. So here I have at the upside, the flow indicator controller, and at the bottom side, the level indicator controller. Just before starting running your process simulation dynamics, is interesting to go to integrator, and we can decrease the velocity of the information that you see in the screen. Here, by standard, it is at 1, there is no acceleration and no deceleration. So what I want to see is slowly what happens, because when we are talking about pressure, when we are talking about flow, usually the changes are very fast, and when we are talking about volume, depending on how much flow we are handling, it can be very fast. So just to verify what will happen, let's decrease a little bit the response in the graphs. And now we can click on run. Remember that for this time, I just have the KP of the process. I didn't add the integral nor the derivative. And just before click on run, I will change for auto. And let's see what happens. So my process is already running, and here I have another way to verify the results, what is happening. If I click on turn, and if I go to monitor, I can verify that my system is very unstable. As you have seen in the first approach to the Ziegler and Nichols approach, it was the behavior that they would like to verify. Cycling, disturbance, and with that do the calculations for the ultimate gain, ultimate periods, and with that define the KP. In this case, I am already dealing with the KP parameter. So what I can do here to have a more stable condition to my process. First thing is that you can see that one point to another, the process, the opening of the control valve is too fast. It goes from 0 to 100%. And sometimes, most of times, when we are dealing with the dynamics in the Aspen Hysys, you will have some kind of abnormality. As you can see, the graph disappeared. So what I will do here, first thing first, I will do the decrease of the KP in order to decrease the response of the system. When I do that, you see that my graph already responded, and I am able also to change the range or the time range that I have here. So let's click with the left side, the right side of the mouse, click on control, and if I go to axis, I can use the auto scale, and I can define also the delta time that I want to evaluate. So here I will increase that to 30 minutes, and in the axis, as I'm talking about the percentage, and I can see all the information in my screen, I will let as it is. Just to have the same effects, let's change also here for 30 minutes. And in this way, we have both graphs at the same basis, time basis. So what I have here? I have here the blue line represents the opening of the control valve. I have the green line that represents the present value of the control valve, and I have the red line that represents the set point. When you are doing when you are turning a PID controller that has only the proportional part of the controller, you will never reach the set point. You will always have an offset if your control loop is stable, or you will have values above and below the set point if your proportional gain is too high, so it is in unstable conditions. So now to get closer to the set point, I need to introduce the integral value for this process. So here at the first site, I will add S1, and let's verify what's happening and observe that we will have changes in this case only in the flow controller, because I'm dealing only with the flow controller at this time. And now the PV already reached the set point. In the Aspen Hysys, it is very easy because there is no effect of environment, there is no effect of the increase in pressure drop because of your pipe or pipelines and etc. So this is a reference to you deal with the controllers of the system, but it is don't represent the real life if you don't have real life data to compare the results. So stay alert with that. So in this case, I can conclude that my tuning to the PID of the controller is okay. So now, just to verify the behavior of the system, I can change the set point. So let's increase a little bit. And let's decrease a little bit. Just to let our life easier, let's use auto scale. Now let's change again. You can see that the red line and the green line matches one with another. So very fast response. To see that slowly, as I told you, what you can do is you can stop and go to the integrator and verify if it's possible to let the system more slower. So let's return and let's do the changes. Now you can see that the graph is slower this time. So you are able to verify what's happening in the control. Another way to verify is to use the monitor and see the behavior of the system, but not the most reliable, but the best way to verify the response is using the chart. So this is how the PID tuning is set in the Aspen Hysys. In the Ziegler and Nichols method, what they mention to you to do the tuning, the procedure that they recommend you to define the numbers for the PID tuning is to let your control loop in manual and add a disturbance. So for instance, here I have a 13 opening, and I will add a disturbance in the system, for instance 45%, and I will verify the graph and look for the dead lag or dead time. I will look for the time constant and also for the gain of the process, because now the set point is not matching with the present value. So this is the way that the Ziegler and Nichols recommend you to define the values for the PID. This kind of the method can be used in the field, but you must be alert about the limits of your system to not go to unsafe conditions. And it depends on the kind of variable that you are evaluating. Because to define the time constant and to define the parameters based on this method, you need to have a stable method, a stable process. But not all the process keeps it stable when we are dealing with the process in manual. For instance, let me return it to auto, and now let's deal with the level. The level is in auto. I didn't set any parameter for integral, so we have only the proportional. So this way you can see that my vessel is empty. And in real life, if the vessel is empty, I need to make sure that my valve is closed, because as I told you, I have a flammable gas. I need to keep the liquid sealing in this vessel to prevent sending flammable gas to undesired conditions. So here I can start on auto. So here I can, as we know, here if I want to increase the level in the vessel separator, I need to close the valve. And here we have a direct response, because to keep the present value at the set point, if my variable increases, I need to open more the valve to keep the same level. So what I can do here to have some kind of level in the system is having on manual, and this opening is too big because I'm not filling the valve based on the amount of liquid that is going into my process. So instead of having 8, almost 9, I will consider 5% of opening. When I decrease the opening, I expect to have an increase in the volume, but I don't reach that. So let's decrease more to 1% opening. Now I'm starting having the increase in my process. So now I starting increase the volume of the level of the vessel separator. And here we can imagine that this vessel separator is too big to the amount of liquid that we have in this system. The calculation or the sizing of a vessel separator depends on two things. The first one is the amount of gas that is going in, because you need to have the velocity that goes to the vessel separator. So it defines the diameter of the vessel separator, and we need to define the hold up time that we want to have, if it is 1 minute of liquid, 5 minutes of liquid, depending on the standard that we are using or the procedure that you have in your company. So I didn't do the sizing of these. I didn't use these criteria to define the size of this vessel. I just add a handle value to do this class for you. So, but you can see now that the amount of liquid is increasing, and differently from the flow controller, if I add one value here of opening, my system will always be increasing, because the amount of flow that is going in is less than the amount of flow that is going out. And I need the PI controller to let the controller able to or close the valve or open the valve to have the best to the level reach the set point. Here you can see that is decreasing, so 1% is too much. So now what I will do, I will go to the settings. Let's define the KP and TI, and let's add it to auto and verify if my system responds. And the set point here was 0, so I want as 15%. So as my present value is below the set point, my valve closed, and now it's increasing the PV. The vessel is filling. Eventually, every time that you change the set point, your controller can have an unstable condition because the calculations of the error, that is the value, the present value, that is the differences between the present value and the set point. So you have seen a bump there, but that's why interesting when we are doing the PID that most of the controllers asks that we let the controller to manual, do the changes in the KP, TI, and etc. And after that, we return to auto. So here, guys, we have the PID controller in the Aspen Hysys.